share that. So, apparently I need more coffee. Well, I don't want to. Oh, that was somebody else. I don't want to keep everybody too long, so I'm gonna start with these because they should be fairly straightforward, and then we'll move on to moles and mass and compounds, glucose or whatever, 6 sugar, 6 carbon, 6 times 60. Hydrogen is 12. Uh, 96. Oh dear. Ammonium. 10, 20, 30, 42. I think it's 3097. Yeah. Well, at least according to that one. And 4 times 16. 7, 12, 10, that's 1, 6, 8, 9, 10. CL. Uh-oh. Gonna use a calculator for that one. And baking soda. Now, ultimately, if you can do this in a calculator for another question, that's perfectly fine. Oxygen is 3 times 16 is... I normally start um, doing it this way because it's the process of making sure you have everything written down, because mistake, like in grade 11, you guys are all capable of adding, you're all capable of naming things and all of that. It's miscounting for something like ammonium phosphate not having 3 and 12. The phosphate's okay. um, I can get all sorts of different, okay, good, elements. It's not 10, 11, 12, 13, 14. Like it's a counting thing that is where most people run into issues. It's not that you can't add. It's not that it's missing elements. And I can string some of these. I could give you people miscount carbons and oxygens. You can miscount different things in different places. So that's the practice part about that. So molar mass to find moles. So the same idea, we have a mole of an element weighs a particular mass, and we talked about molar mass, which is the mass of a mole of, in this case, sodium hydroxide. We use the molar mass to do our mole conversion. So the first thing we need to do, find the molar mass. So sodium is 2299, hydrogen is 1.01, and oxygen is 30, 40. This is one of the handful of element or compounds that it's the molar mass is stuck in my head. Water is simple, some of the simple ones, but sodium hydroxide, because it's 40. So how many moles are there in, the grammar there is horrific. So you're always going to be given a number, 5.69 grams sodium hydroxide. Our first step, always going to be there. We are given grams, we want moles. So that tells me if I want moles, I put it on top. I'm given grams, it's got to go on the bottom. Usually the unit you want is on the top. That's not mole grams. The unit what you have is on the bottom. There's some cases where you've got reciprocal units and different things. But this is generally for mole calculations. 1 mole weighs 40.00. Break out our trusty calculator. 3 significant figures, 4 significant figures. If there's a decimal, any 0 at the end counts. So we get 0.142 moles of sodium hydroxide. And that's a mole conversion. When we do stoichiometry after equations, we're going to add a little bit, but that's okay. So potassium nitrate, same thing. I don't know why I just wrote it all again. Potassium is 39.1. Nitrogen is 14.01. 3 oxygens, 316s are 48. 0.11s, 17, 21. Carry the 2, 9. So potassium nitrate weighs 101.11. If you have 100 grams of it, you have a mole. How many grams would you have if you have 0.865 moles? Well, we're given 0.865 moles potassium nitrate. We want to know mass, which is grams. So I want grams in my numerator. I want to get rid of moles. Well, I know 1 mole has a mass of what we figured out up there, 101.1 grams, so we're looking at like 10 grams. So those are some questions you'll get later. 0.865 times gives me three significant figures, 5. So I want 1, 2, 3, 87.5 grams of potassium nitrate. So those are the two calculations. I have a couple questions here. I can't, because I don't have the textbook handy. It's upstairs, hiding in a closet. Those are representative sort of questions for those. Were we in class, I would probably do those two and say, get these ones or the ones over here done. I may do one of each of those in a second. I'm going to do gases in the mole quick because this is actually fairly straightforward. And this is why it's called Avogadro's number, because Avogadro was the guy back in whenever it was, the 16, 17, 1800s, I can't remember, probably 17 or 1800s, that if you have a flask, ball, balloon of gas, and you have two of them, one is helium and one is argon. If they have the same temperature and the same pressure and the exact same volumes, they have to have the same number of particles. And they're going to weigh different because, well, 1 mole of helium is going to weigh 4 grams. 1 mole of argon is going to weigh 20 and change, I think. Periodic table 20.2-ish. So back then it would have been like 20. But the problem with gases is it's hard to weigh a gas. You can do it, but you have to have a balloon or some sort of flask. You have to have a balance that's going to be steady enough that the balloon isn't going to blow away and all of that, and you have to weigh it first, and it's a little bit tricky. So the simple way, at what's called standard temperature and pressure, they're different depending on the way, so we measure pressure or volume or two things that have an effect on the volume of a gas are, well, this, we measure volume. This is, there's something that we would, I might have time to mention for like 10 minutes. It's called the ideal gas law, which relates pressure, volume, moles, some constant, and temperature. Well, the pressure of a system, the volume, the amount of stuff, and the temperature, those four things are all nicely related, unless it's really cold or really hot or high temperature, high pressures and whatnot, by that relationship. So you can do that if this is the same and this is the same. Well, that's a constant regardless. The volume is proportional or related to how many moles there are. So we do this at what is called standard temperature and pressure, which, whoops, is actually not a super practical one because 1 atmosphere of pressure is kind of the overall average pressure that you should exist or feel at sea level at a normal day. I mean, the atmospheric pressure changes day to day based on weather and all sorts of things, but on average, it's they call 1 atmosphere of pressure, which is related to the standard the SI unit of pressure, which is a kilopascal, which is Pascal is 1 Newton from physics per meter squared. Kelvin, it's the same temperature scale as Celsius. So 1 degree Celsius and 1 degree Kelvin are identical in terms of the jump. But when we do things with temperature, this 0 in Celsius causes trouble because if we're multiplying or dividing by 0, things tend to go bad. So we use this Kelvin scale, which is an absolute scale. 0 is the absolute lowest possible temperature. 273, just because I'm picky. The freezing point of water, or 0 degrees, is 273. And that way, we avoid that whole 0 business. That's just kind of an FYI thing. It's something that you're going to need to know if you take Chemistry 12. 0 degrees Kelvin is impossible to get to for a number of reasons, not necessarily physical. It's kind of a theoretical concept. Um, but it's just an absolute scale. It's something to state. We say this is STP, and our conversion factor for these is at that condition, 1 mole of gas will have a volume of 22.4 liters. So think of if you had a volume, if you had, what, 12 and a bit pop bottles, 11 and a bit pop bottles, and it was 0 degrees out and the pressure was great, and you filled them all up with air, you would have 1 mole of air. We call it a molar volume. There's another one. This number is usually the back of your periodic table somewhere. It's oh, here we go. STP 0 and 0 Celsius and 101.3. V at STP is 22.4. Then we have this other thing down here. It says SATP, which is standard ambient temperature and pressure, which if we look up here, instead of 0 degrees Celsius, which nobody works at that, why don't we go up 25 degrees? Now, having done it, working in a lab that's 25 degrees Celsius sucks because you usually have things going on and you have to wear a coat and pants and this and that. So it's actually, they call it ambient, but it's not really. It's actually quite, lab, a pain in the butt. But those are the two kind of numbers. Where did my notes go? So that's a whole bunch of me going and waving my hands. What is the volume of 4.59 moles of carbon dioxide? Whoops. Or oxygen. Or argon. Or any gas. Doesn't matter. Could be xenon or krypton or whatever. 4.59 moles of carbon dioxide. What volume? So I want liters of carbon dioxide. Same thing. I want liters, so liters goes on top. I want to get rid of moles, so moles goes on the bottom. Moles and moles cancel. We're left with liters. We know it says at STP 22.4 liters of gas would be representative of, or 1 mole takes up that volume. Multiply significant figures, 103 liters. So none of these calculations are overly complex. I can do the same thing. How many moles are there? Liters of neon. How many moles of neon is that? So I want moles, so I want to get rid of liters. So those cancel with those. And 1 mole has a volume of 22.4. I divide that, and we're going to get like 3.8 or something. 3.73 moles of neon. And those are questions that involve this sort of thing. So I'll pop these out. What's over here? Huh? That's where we just were. Those are the answers to 16, 17, 18, 19, 20, 21. Which is those plus those. I'm going to go through and do 1 and 3 because they're easy to weigh up. How much would 1.27 moles of ammonia weigh? Nitrogen. 3 hydrogens is 17.04. I want grams of ammonia, which ammonia is usually a gas, so you would actually probably want liters, but this says weight. So I want grams. I want to get rid of moles. Moles of that cancels with moles of that. We know this is 17.04 grams in 1 mole. $21.6, not 26.1 grams. So you have almost 1.25 moles of ammonia. You would need 21 grams. How many moles are there in 4.31 grams of water? So 4 milliliters of water. 2H is 2.02. This is another one that I'm just writing down because even though I know it, 18 grams per mole. I have grams. I want moles, so grams and grams cancel. 1 mole weighs 18.02. .239 moles, which seems like a relatively small number until we remember that a mole is an Avogadro's number worth of particles. So even though it's that many moles, in that amount, that 4 milliliters of water, there is, oh dear, 1.4 times 10 to the 23rd water molecules. So that's still a lot of molecules because they're very, very tiny. So those are the kind of examples I wanted to go over today. I'll put that back down. There are questions. It was 16 to 19 and then to 20 something down on the bottom. I'm going to post this sort of later. I'm going to probably simplify it, cut a couple of them out, because if you can do some of these, you can do them all. I have to delete number 7 because we're not going to get to that. The balloon holds 13 liters of neon. How many moles are there? What volume would that occupy? Determine the mass of 1.024 moles of that. how many moles are there in those. Some of these, excuse me, you have to write the formula out, but it'll be a variation like that, which is just a variation on those kind of four examples. 16 to 21. Calculate a mass, calculate a mass, calculate moles, some volumes. 17. I'm not sure. Whoa. What's going on there? But that's kind of where I was hoping to get to today. There is some other stuff in here which we'll come back to if we have time. Percent composition. What percent is stuff? We can do it based on formulas and empirical formulas, which are somewhat important, but like that's 3 days worth of stuff that we need to balance equations and do stoichiometry before we can worry about that. So find a molar mass. Molar, if you are given grams, grams goes on the bottom. If you are given moles, grams goes on top. It's just a matter of answering that handful of questions or taking a look at them. You don't necessarily have to ask them all. Not sure why that keeps coming up. So, I don't know if we lost anybody or not, or people forgot because it was Monday. But that's all I have for you this afternoon. I'll post that sort of assignment. I'm pretty sure tomorrow I'll go over some of those questions and start looking at balancing equations and reactions. And yeah, that's kind of all I had for today. Wait, unless anybody has any questions, you are all free to go.
Thank you.
You're welcome. Thanks for coming. Welcome. I would say enjoy the weather, but it's raining. And there you go.